Okay, we're going to talk about nuclear chemical reactions today. Before we get going, we should talk about the particles that we might see emitted from a nucleus. And these are the basic ones. A nucleus that's unstable might emit a proton, and a proton has a proton count of 1. So I always refer to this lower number as how many protons something has, and then the upper number is the mass. So a proton counts for 1 atomic mass unit and 1 charge unit. Neutrons, on the other hand, have no charge, so they don't count as a proton, but they do have the same mass as a proton. Electrons are oftentimes emitted from a nucleus. They, as you know, have a -1 charge, but for all intents and purposes, 0 mass. Now, many textbooks will use the E for an electron. Some textbooks will use a beta, the Greek letter beta, to represent the exact same thing. The opposite of an electron is a positron, so it is a particle with essentially no mass, but rather than having a negative charge, it would have a positive charge. So it generally is represented with an E, although I've seen textbooks that will use the Greek letter beta with a plus next to it. Alpha particles are a common particle emitted from the nucleus as well. They count for 2 protons and a mass of 4 units. Which essentially makes it a helium nucleus. So helium is in box number 2, and the most stable isotope has a mass of 4. There are some very energetic particles that are emitted, including gamma particles and X-rays. These are essentially electromagnetic radiation, and these are emitted when a nucleus has excess energy that needs to be lost. So in order to attain a stable energy state, it has to lose some energy, and quite often this is lost as either gamma or X-ray particles. One thing to mention about all of these is the smaller a particle is and the faster it's moving, the more damage it can do. So you're well aware that X-rays can penetrate through your body. They have no mass, but they're moving at the speed of light. The same with gamma particles, even more energetic. And then it kind of goes down from there. The bigger it is, the less penetrating power it has. So things like beta particles and positrons are very small as well, so and moving very fast, so they can penetrate quite far. Neutrons and positrons less far, and then big alpha particles, they barely penetrate at all. And just a sheet of paper or even just a dead layer of skin on your epidermis is enough to shield you from alpha particles, but the other particles would need a little bit more protection to keep you from harm's way. So you know that when you're at the dentist's office, they oftentimes, or they should, throw a lead shield over your chest to protect your vital organs from exposure to X-rays. Okay, so let's talk about the basic anatomy of a nuclear reaction, and there are some things to keep in mind in a nuclear reaction. So here we've got the radioactive decay of carbon-14 to nitrogen-14, and in the process an electron, or better known as a beta particle, is emitted. So if I take a look at the upper numbers, the mass numbers, I can see that the conservation of mass is essentially conserved here. So we've got 14 mass units on the reactant side of the arrow, and I have 14 mass units on the product side of the arrow. The lower proton count or charge count needs to add up as well. So I've got 6 positive charges on the reactant side, and on the product side I've got 7 positive charges and 1 negative charge, which add up to a total of 6. So as long as my mass and charge balance, I should have a good nuclear reaction. So when I'm balancing nuclear reactions, what I'm doing is trying to find the missing particle, and I kind of do this one at a time. So I look at the mass first, and I say I've got 218 mass units on the reactant side, and on the product side I've got 214, which means that I have 4 missing mass units. When I look at the charge count on the reactant side, I've got 85 positive charges, and so far I'm only showing 83 positive charges on the product side. So I must be missing two positive charges, And if I look back at that previous page where I listed all the particles, the one that has a mass of 4 and counts for 2 protons is the helium nucleus, or the alpha particle. Let's do it. So strontium-90 can decay to produce a beta particle, and when I'm trying to balance this out, I see that I've got 90 mass units on the reactant side with strontium there. And so far I'm showing 0 mass units for the electron that's emitted, so that means whatever is produced as a daughter particle is going to have 90 mass units. On the product side, or on the reactant side, I've got 38 positive charges. So far I've got a -1 charge on the product side. So to get that to balance out, I've got to have 39 positive charges. I look in box number 39 on the periodic table and see that it's yttrium. And that's just the basics of it. You know, all you have to do is balance the top numbers and the bottom numbers. And if you're missing what the isotope is, just go to the periodic table and look in the box that corresponds to the atomic number that you just figured out.